Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin. I'll be running through part 2 of problem set 15, valence bond theory. Okay, number 4, state the hybridization of the central atom, the molecular shape, and the bond angles for each of the following molecules, and then use these for the bond angles. Now, in order to get the correct answer on this, in terms of both the hybridization and the shape, you have to draw the correct Lewis structure. If you do not know how to draw the correct Lewis structure, you will get the problem wrong, even if you've mastered how to get hybridization and molecular shape, okay? So make sure that you know how to draw Lewis structures correctly. In this case, this would be the Lewis structure for the CH3F with 3 lone pairs on this fluorine. So now, I'm gonna skip hybridization for a second, because if we know the molecular shape, it's actually really easy to figure out the hybridization. So the first thing you need to know is figure out the steric number. The steric number is lone pairs. I'll just put LPs plus bonds. Okay. So in this case, I've got 1, 2, 3, 4 bonds on the central carbon. So I'm going to put the steric number as 4. Now, if you remember the steric number of 4 on that chart that we did, I'm not showing it here because I'm assuming that you've memorized it, and that's something that you have to have memorized for the test. So, but assuming that the steric number is 4, the electron pair geometry would have been tetrahedral, and there are no lone pairs on this guy. So actually, the molecular shape ends up being tetrahedral. Okay, tetrahedral. Okay, and that means the bond angles are going to be 109.5, meaning the bond angle between each bond here is going to be 109.5 degrees. And then the hybridization will come from the steric number as well, okay? So the steric number, as long as you've drawn the correct Lewis structure, will tell you both the molecular shape and the hybridization. So the hybridization, remember that we have an s orbital, 1 s orbital, and 3 p orbitals, okay? Now, these are arranged in a way that we can't really use them in bonding right now, okay? They're in this weird, we've got this p orbital coming up and down on the side and in and out of the page, and then this random s orbital in the middle. The s orbital in the middle is kind of covered and can't really make a bond. And remember, carbon can make 4 bonds, and so the fact that this s wouldn't be able to bond doesn't make any sense, because if you fill in the valence electrons for carbon, we get this. But in this model right here, this would only indicate that 2 of the p orbitals are bonding, but we know that every carbon makes 4 bonds, and so we have to account for how carbon might make those bonds. So this is what happens. When we have a steric number of 4, what carbon does is it mixes 4 orbitals. In this case, we got 1 s orbital and 3 p orbitals. And what they do is they kind of mix into orbitals that have energies right between them. So we mixed 4 orbitals together, we get 4 out, and we call these sp3 orbitals. sp3. And now carbon with its 4 valence electrons, now it makes sense, shown this way, that it can actually make those bonds, because we need each of these to be half-filled orbitals in order to make bonds, right? And so that's what it's going to do. And so this, we would say the hybridization on carbon is sp3, okay? So that's going to work out for pretty much anything that you hybridize. You're going to have to figure out how many orbitals are mixing, okay? And what's left over, because sometimes if you still have a pair of electrons, that may be a lone pair, or if you have an empty orbital, that may be an empty p orbital, or whatever it may be. Okay, so you have to make sure that you know how to look at this. So let's look at some more examples for this. So BRF5, so BR, I'm going to draw the Lewis structure. I'm going to assume that you know how to do this, so I'm just going to draw the Lewis structure and assume that you know how we got there. Okay, so this is the Lewis structure. So the steric number here on this molecule is 6, right? We've got 5 fluorines, 5 bonds around the bromine, and a lone pair. So that's 6 for the steric number. So in terms of the molecular shape, if you remember, the electron pair geometry would say this is octahedral, but we've got a lone pair, right? And so this ends up turning what we call square pyramidal. Because if you remember, for a steric number of 6, we have an axial and an equatorial plane. Okay, equatorial meaning it's flat in the middle. And the central atom, let's say put a C, is bound to all 6 of these areas. But when we have a lone pair, it actually goes on the axial plane here. It doesn't always go on the axial plane, but in this case it does. And so you can kind of see where we get this structure. It looks like it's a square pyramid, right? So we call it square pyramidal, which means the bond angles, knowing that there's a lone pair here, it was 90 degrees, and now it's slightly less than 90 degrees, okay? And now comes the hybridization. So in hybridization, notice that we have 6 orbitals, and before, remember, we only have 1 s orbital and 3 p orbitals, so we have to think about what other orbitals are going to be there. And remember, bromine is in past the 3rd period, And so it has open d orbitals, and this is why this is how we justify expanding our octets, because we have these open d orbitals up here. So bromine needs 6 orbitals to hybridize. So it's got 1, 2, 3, 4, 5, 6. So in this case, they're going to mix all these together, and this is going to become an sp3d2 hybridized orbital. That would be the hybridization, because that's how it can make each one of these bonds, and it's going to make this bond and going to make that bond. We're not going to leave anything unhybridized. There are no double bonds or anything here, so that would be our final answer for that one. Okay, hopefully this is starting to make sense. We're going to do a few more examples, and then hopefully it starts to clear up a little bit. Number 5, state the hybridization of the central atom, the molecular shape, and so the same instructions here. So I'm going to draw this the Lewis structure again, and just assume that you know what this looks like. So, or that this is the correct Lewis structure. Okay, so there's my Lewis structure. Now the steric number here is 4, which means the molecular shape, or the electron geometry. I'm gonna include electron geometry in this one, is tetrahedral. I'm just gonna put tet here. But we've got 2 lone pairs, right? We've got 2 lone pairs in there. So this is actually the bent version. This is bent, which means the bond angles here are less than 109.5. Okay, and that comes all from that chart that we covered. That's just, like I said, that you're just gonna have to have that memorized for the test. So now, in terms of the hybridization, our steric number is 4, so I'm going to put, I need 4 orbitals, right? So I'm going to say sp3 again. Okay, sp3 hybridized. That's 1, 2, 3. All right, last one, XeF2. So Xe, xenon, is kind of one of the funky noble gases. It actually it can make some bonds, and it actually expands its octet to make some molecules. So we got this F over here, and this F over here, and actually has 3 lone pairs on the center xenon here. And this actually minimizes the formal charge, so we don't have to, there are no formal charges on this guy. And so let's figure out the steric number here. The steric number here is 5. So the electron geometry should be trigonal. This is called trigonal bipyramidal. Because it also has if I have the center atom here, it has that equatorial axis. So right here and here. So it's got a bond going like in a triangle here. And so it kind of looks like a triangle pyramid on top of another triangle pyramid, kind of like that. So that's why they call it trigonal bipyramidal. But the molecular shape, actually, let me put that structure back up there. The molecular shape, if you look, when we have 3 lone pairs around the center atom, they actually go on the equatorial plane this time. So you can kind of see that if there's a lone pair here, a lone pair here, and a lone pair here, that this just looks like a straight line, and it is. And so it ends up just being linear. So the bond angles here are just 180 degrees. Now, just the hybridization is left. So notice that xenon is past the 3rd period, and so we're opening up some d orbitals, right? Because the steric number is greater than 4. So in this case, I'm using all 5 of these orbitals. So this is going to be sp3d hybridized orbital. Now, there's not going to be a hybridization past sp3d2 in this class. We're not going to be dealing with anything above that. It's kind of beyond the scope of this course. But you will need to know everything from sp to sp3d2, okay? All right, last kind of problem related to this. So state the hybridization of the central atom molecular shape, same instructions here. So I'm going to put chlorine here in the middle, and then again, I'm going to assume that you know what this looks like. So I'm going to put... All right, so this is what this looks like. Okay, you can see that this would have resonance structures, but we're not going to do that for right now. Okay, so let's start with the steric number. The steric number here is 1, 2, 3, 4. Okay, so this is a 4. Steric number is 4, which means the electron geometry would be tetrahedral, but the molecular shape, given that there's a lone pair here, is going to be trigonal pyramidal. Okay, which means the bond angles here, based off the tetrahedral, is just going to be less than 109.5. Okay, so now steric number 4, that means I'm going to need 4 orbitals, so that is sp3 hybridized right there. Okay, now it's interesting because even though this is sp3 hybridized, we have double bonds, right? And typically we think of double bonds as being overlapping unhybridized p orbitals, but they can actually, in this case, will also be overlapping unhybridized d orbitals to make those double bonds. All right, last one. Until the 1960s, of all the noble gases were thought to be totally unreactive. This change was made when Xeon F4 was made. Okay, now they want us to draw the Lewis structure of Xeon and F4. So if you remember, I'm going to assume that Xenon, because it's in the third period or below, can make can expand into octets. So I'm going to draw the fluorines around here, each with their octets. And if you do it correctly, actually, let's just do this since we're going through the process of drawing the Lewis structure. We needed 8 electrons here and then 7 times 4 here. So that's going to be a total of 36. And in the structure I have shown, there's only 32, right? Because of each bond is 8, so there's 4 of them. It's 8 times 4 is 32. So I actually have to put 2 lone pairs on the center atom. Okay, so that's the Lewis structure of Xenon F4. Now, they're asking for the electron geometry. That's just based off the steric number, which is 6, right? So that means this is going to be octahedral. I don't have to look at any lone pairs yet until I get to molecular shape. Okay, but the molecular shape, when I have 2 lone pairs like this, on the axial plane, the lone pairs actually go on the axial plane in this case. So instead of where we have, this guy out here like this, here's my equatorial plane, here's my axial plane, and here's my equatorial plane. Then what we need to figure out is whether if this is gonna what would this would look like. So if the lone pairs are here and here, then you can kind of see this is actually going to be a flat structure. This is actually called square planar. Because all it is just a flat square, because this lone pair is just pushing down, but this lone pair is equally pushing the other direction. And so they actually just end up making this square structure. And this is one of the few that ends up, even if you have polar bonds, which in this case we actually do, this would be a nonpolar molecule because they all cancel each other's vectors out. Okay. So now they're asking for what the orbital hybridization would be. If our steric number is 6, that means I need 6 orbitals, which is sp3d2 hybridization. Okay. All right, last question. Based on your knowledge of the atomic structure, electronic structure of xenon and fluorine, briefly explain why it is not unreasonable to think this compound could be made. Really what they're asking you to think about is expanding octets, okay? Expanding octet. So I'll just put xenon can expand its octet. So let me just, right here, expand octet, okay? Because it's past the third period, Now, that's really the only justification that you would need for this, because that's the only way that they can make these kinds of bonds, and xenon just happens to be past the third period. All right, I hope that was helpful. We'll see you in the next problem set when we talk about molecular orbital theory.